Hi everybody, Simon Whiteley here. Welcome to my next live stream. So today we're going to be talking about a space case study to do with the Boeing Starliner spacecraft taking part in a NASA crewed mission, so a test mission. And essentially we're going to go through the investigation report and get through about an hour today, maybe a little bit more, where we'll read through the report, talk about it through the lens of STAMP, STPA and CAST. And then, of course, if you've got any questions, comments, please type them in the chat on YouTube, and I'll bring them up on screen and I can address those as we go in. This is the first time, well, it's not the first time I've used YouTube to do live stream, but it's the first time I've used YouTube for a live stream for a little while. So I'm just going to see how this goes, see how we get on, and just bear with me. I think there is a delay of about 30 seconds. So it's not quite as big a delay as it is on LinkedIn, but we'll see how that goes. Please write in the chat. Let me know you can hear me, and if you can type in the chat and let me know where you're watching from, that'd be fantastic. And of course, if you've got any questions, please stick them in the chat, and I'll get to them as we're moving along. So yeah, let's just have a look. Have we got? We've got a viewer. Fantastic. Hello, viewer. We'll see how many more viewers we get by the end of today. Now, of course, normally I've done these on LinkedIn. So if you're not already connected to me on LinkedIn, please visit LinkedIn, search for my name, and we can connect. And of course, if you need help and support with STAMP, STPA, or CAST, then please visit my website. And I'll just quickly show you my website now. There we go. So we choose full screen share. Look at this, fantastic green screen. Yeah, if you visit my website, Whiteley-Safety.co.uk, there's a really big. It's this side, a big green button. You can press that. It says, I need help now. Stick your details in there. Send me a message and I can set up a call and we can have a conversation. So this is a picture of the Starliner. It's a spacecraft. I'll be honest, I don't know too much about it. Reading this report will be the first time that I've really been exposed to this. So if you're not familiar with it, or if you are familiar with it, please bear with me. Of course, I don't know much about it yet, and what I'm learning is from the report. So the things that I say, the opinions I form, are based on a very small amount of knowledge. Now, of course, this should be a testament for the stamp-based approaches. So as we're going through this case study, and I expect we're going to be spreading this review over a number of live streams. The live stream I did for Cranfield recently, preparation for a Cranfield course I was supporting, I think that was 5 live streams, about 10 hours or so of content. This report is 311 pages, so it's a lot bigger. I probably won't need to read all 311 pages, but there will be a lot to read and take in. And so, of course, I'm going to go through that live stream as many times as I need to get through the report. And then I'm going to put together a case study and make that a video, probably present it on a live Zoom. So if you want to join me on Zoom live and we can have Q&A live, we could do that. But yeah, the intent is to go through the report cold and essentially review it, think about it through the lens of STAMP, STPA and CAST. And I think I've repeated myself there, so just bear with me. Okay, so the official investigation report was released in February 2026, I believe. And the incident itself occurred in June and beyond 2024. So this is the official investigation report. Starliner propulsion system anomalies during the crewed flight test investigation report. There's the members of the investigation team. And actually, just to put a fine point on that, the things that I say in these live streams are not intended to be criticisms of individuals. In fact, I'll do my best not to criticise individuals because that's not what it's all about. It's really looking at the report and then seeing what else we could possibly learn if we were to use STPA or CAST. And of course, as I said, I don't know too much about the thing itself. I don't know too much about the organisation. Boeing in this case is the designer, and I don't know too much about NASA and how they do mission control and make decisions with regards to the design. So of course I'm going to be coming at this completely lay. So please, if you are some of these people involved in this, don't take criticism to heart. I'm here to try and learn as much as I possibly can and share that learning with other people. So as I say, the report is 311 pages. It was released in February 2026. And what I'll do now is go quickly through the exec summary, We'll have a look at the table of contents, the structure of the report, and then if we get time, we'll start going into the first part. In fact, actually, let's just have a look at the table of contents now then. So let's just get it on the screen so it's big enough for you to see. So we've got a number of sections. So, of course, the executive summary, that's always helpful. When you're trying to learn how to do and develop your skills as a stamp practitioner, one of the things that I like to do, and this is what we're doing today, is to go through an investigation report that's relevant to me, what I want to learn, excuse me, and just start with the executive summary. Read through it, try and identify the relevant losses and hazards that occurred, recognising that the definition of hazard we use in STAMP is very specific, and I'll talk a little bit about that later on. And then try and identify the elements of the control structure or the components in the control structure. So we've got controllers, we've got interactions amongst controllers, we might have some actuators or sensors, and we're going to have a control process, or maybe more than one control process, depending on how we as modelers decide to model the control structure. And so the purpose of reading through the executive summary is just to help practice that thought process and really develop those critical thinking skills. So in terms of section 1, we've got the scope of the investigation. So this is, 2 pages. Then we've got additional investigations. So there was a STAR report, summary and findings, and then Boeing's enterprise root cause corrective actions process. Now, I'll just make an observation there. That they mention a specific process, root cause corrective actions, I will be keen to understand whether that is a root cause analysis in the traditional sense, or whether they incorporate STAMP or perhaps CAST as part of that investigation. Now, I know STAMP is quite popular amongst various parts of Boeing, but I don't know whether it would have been popular and used as part of this, so that's something we'll discover together as we go through this. And of course, if they're not using STAMP and CAST and STPA, of course, I'm going to recommend that they at least consider having a go with it and seeing what they can find. And I'm hoping that perhaps if they were to watch this, watch these live streams, they might get some inspiration and actually have a go themselves. And of course, if you want some help, let me know and I can come across and give you a hand. Section 3, the Commercial Crew Program Background, so the CCP, and they talk about orbital flight tests, OFTs, and then we've got Section 4. So Section 4 is, well, it's quite large, as you can see. So this is the technical root cause analysis, and again, RCA, so I'm taking it that STAMP, STPA or CAST has not been used to influence that. So we've got objectives and approach. Oh, we've got a fault tree, everybody. Fantastic. So fault trees. Fault trees focus on mainly failures. They're not particularly good at including human factors and software. And of course, STPA helps to deal with those things. So if they're using fault tree analysis as the prime safety analysis method on this particular platform, then it's probably about time to have a go with STPA as well. And again, I am aware that some parts of Boeing are using STPA, so maybe they'll do that in the future. We don't know. Then there is 3 parts to the analysis. There is analysis of I think it's the command module reaction control system jet failure, and you'll notice that this focuses on failure. Maybe, and we don't know yet because we've not gone through the report, it's always possible that there are some unsafe control actions involved in there, and they may not be due to failures. They might be due to what I call dangerous successes. So the system has behaved as designed. So it's not really appropriate to call those conditions failure. And maybe this situation is just all about failures, but I'd probably suggest there might be some dangerous successes in there as well. So we need to keep our eyes peeled for those. And then the next one is the analysis of the 6 degrees of freedom control. So the something module, service module, there we go. Service module reaction control system jet failures. Again, that'll be interesting. And then there's the analysis of a helium leak, and then an analysis of the deorbit capability fault tolerance. And then there's some common observations and organizational factors. And then if we zoom over to this page over here, we've got section 5, which is culture and decision-making process during the mission. Now, of course, if you're familiar with STAMP and STPA and CAST, one of the key concepts is what's called a hierarchical control structure or a safety control structure. And this topic of culture and decision-making process is something that can be explicitly modelled using the control structure to understand who are the stakeholders, how do they interact with each other, what are their safety-related roles and responsibilities, and what are what is their authority and accountability, and then of course what are the control actions and feedback amongst them, and how does that influence their decision-making. And then, of course, root causes. There we go. There's the root causes. So there's going to be a number of those. And again, the language of root cause analysis suggests that STAMP has not been anywhere near this. Additional observations from the investigation team, consolidated recommendations, and then there is a helium fault tree. There we go. I've already talked about fault trees a little bit, so that'll be interesting. And then the service module reaction control system fail-off fault tree. Now, if I remember correctly, these fault trees are a little bit blurred in the report, so we can't really tell what there is. So there's probably going to be limited things we can say about that, other than to say, like I've said before, if you're doing fault tree analysis, supplementing that or including STPA in parallel to a fault tree analysis is a good idea. And of course, I've reviewed many fault trees over the years, and one of the challenges I always find with fault trees is they do miss things. They are failure focused, and of course they won't identify dangerous successors, which STPA will also identify. And of course, it's not particularly good at dealing with human factors, software, and the system behaving as designed. Okay, there's a number of appendices, quite a few, 9 appendices. So we've got human factors, we've got the Likert scale survey data on team effectiveness, we've got some references, acronyms, tables and figures, organisational trust plan, investigations team chartering memo, the CCP STAR report, so that was the other investigation report, the Boeing root cause analysis summary, and then the senior review panel response to the investigation team report. So yeah, we'll have a look at some of those. I'm not intending to dig into all of them, but we'll see. So that's sort of where we are with the table of contents. Let's just have a quick look at the chat. We've got some chat in there. Hi Tom, Thomas, great to see you. Thank you for coming along. Let's have a look. So what's Thomas saying? So FTA can take advantage of software and human failures. Okay, yeah. Clifton Erickson, retired from Boeing, developed the fault tree analysis tools for software analysis. Fantastic. Yeah, I've got his 2 books actually, good books. If you were, if you're not aware of Clifton Erickson's book Hazard Analysis Techniques, and then the later version of it, I do recommend picking up a copy of that book. It is a good book. I do recommend it. Thomas says, where fault tree analysis fails is evaluating the management decision making that contributes to events. So yes, STAMP can certainly deal with that explicitly. So thanks for that, Thomas. Thanks for coming along. It's always great to see you. Right then, so you'll notice that there's loads of scribble and colours and things and lines over this. So I've already read through the executive summary the other day. I think it was Monday or Tuesday. And I've gone through and just highlighted a few things just to get the juices flowing in my mind. So what I'm going to do is I'm going to read through this executive summary, and then I'm going to explain what these different lines are, just to help you understand the mindset behind what I'm doing. So as I said, one of the things to do when you're reading any information is always try to spot the candidate. How can I say this? Always try to spot the candidate controllers. So when I say candidate controllers, what I mean by that is you're looking for entities or stakeholders that make decisions and provide control actions. And essentially thinking about, well, are they candidates for inclusion as controllers in my control structure model that I'll eventually build? And so, of course, this is a bit of a skill that you have to develop over time. It doesn't necessarily come naturally to everybody. Sometimes it's really obvious. If you're talking about a car accident, an automotive accident, you've typically got a human driver driving a vehicle. And apart from issues with the vehicle, usually it's due to inadequate control on the part of the driver. Now, of course, if you introduce an automated driving system or a self-driving autopilot, so to speak, into that vehicle, then all of a sudden you're adding an extra controller into that structure, that can contribute to inadequate control and accidents. And of course, you can have situations where those two controllers either interfere with each other or potentially think that the other controller is in control when the other one actually isn't. And that can be a contributor to accidents. So all I'm saying is when you're reviewing these things, just try and listen out, look out for these candidate controllers for consideration for inclusion in your control structure model. And of course, you're not trying to build the most complex model in the world. You're trying to build a model that makes sense for you as the modeler, and doesn't get too overwhelming. You have the decision about how much detail, what level of detail you want to include. Candidate controllers, that's what we're looking for. And of course, we're also looking for information related to time, because this is an investigation report, and so there'll be a sequence of events that have been captured, or should I say an opinion of the sequence of events will have been captured in this investigation report, which may not match the actual case of events, depending on the resolution of the data they have available, the data sources they have available. But I do recommend highlighting those points that mention time, so that you can create your own timeline, create a mental model of the sequence of events yourself. And then again, also look out for control actions or candidate control actions. And these could be obvious unsafe control actions that have contributed to this particular accident, bearing in mind that when we're talking about an accident, it's more appropriate to use the term contributory control action, because of course we know that this control action is unsafe because we've got the benefit of hindsight, whereas the individuals, the stakeholders, controllers involved may have had no idea that the action they were going to take would result in an accident. So it's not really appropriate to refer to those as unsafe control actions. So as we're going through it, just try and look out for those control actions and whether they're candidate, unsafe or contributory control actions. And then of course always be on the lookout for potential feedback that has an implication for a controller that might explain why they provided the control actions that they did. I think that's about it, isn't it? Yeah, there we go. So and I'll explain the colours as we go, just to sort of emphasise things. There is a method to the madness, so bear with me. So let's zoom in, see if my mouse still works. Okay, so let's make sure that that's big enough on the screen for you. That should be okay. So then, first off, the Boeing CST-100 Starliner crewed flight test launched on the 5th of June 2024. Now before I continue, I'm just going to talk about why I've chosen the dark orange colour. Now when you're going through these reports, this source of information, you're going to identify these candidates as candidates for inclusion in your control structure model, candidate controllers. And some of them you might think, well, they might be relevant, they might not be, and some of them probably definitely are. And so what I do is I highlight them either in a lighter orange highlight or a darker orange highlight to signify whether I've captured them as actual controllers in my control structure model, my draft model, if you like, my preliminary model. So this one I've highlighted. Boeing is a manufacturer, so they are they have the role and responsibility of doing the safety assessment and system safety engineering of that product. And that product in this case is the CST-100 Starliner. So that is a candidate for inclusion in our control structure, which I have, because that's the spacecraft which is ultimately under the control of the automation and the crew, the astronaut crew. And then crewed flight test. So I've highlighted that as dark orange because that is a type of control process underneath, in this case, the NASA organization. So the ground control, for example, they will be controlling that mission. But that crewed flight test also represents a phase in an overall program, which is under the control of some kind of program management. And logically, that program management will be made up of NASA, but it will also be made up of Boeing representatives, and they will coordinate with each other with regards to design information, operational readiness, test results, things like that. It launched on the 5th of June 2024 under NASA, so NASA is going to be a candidate controller, and it's under the Commercial Crew Program, which again is a type of control process, arguably, depending on the level of abstraction you choose. And then this was a pivot. I can't speak today. A pivotal mission in certifying the United States commercial vehicle for transporting astronauts. So I've highlighted them. They are going to be candidates in my control structure, certainly. And of course, that name, that label, at this stage, we don't know if that's one or many astronauts. I mean, we know it's two later on, but obviously, when we're just trying to identify these candidate controllers, we know that that label might represent one or more. So we might have to expand upon that and add extra detail if it's appropriate. We're not trying to model everything to the nth degree. We have to choose an appropriate level of abstraction, an appropriate level of detail that makes sense to us, but also our audience. Bearing in mind that as system safety engineers, as investigators, we will build control structure models for ourselves, for our own benefit. But of course, we're going to have to communicate those to other stakeholders, whether that's other stakeholders in our organisation, maybe to management, leadership, who don't necessarily need to know or understand the detail. And of course, if you're going to produce a report that's going to be seen by members of the public, for example, you need to make sure that you present your control structure model in an appropriate level of detail to be able to communicate with them. But of course, and most importantly out of all of that, you've got to understand that when you build a control structure model, because it contains potentially real information, it could be of use to an adversary or an enemy. And so potentially these models need to be potentially classified or subject to some kind of information control. Because of course you don't want to create these fantastic models that show lots of detail and then someone who's got inappropriate goals perhaps to try and describe it in a less political way, but they might have nefarious goals and you don't really want to do their work for them, or at least let them have access to this valuable work. So just be mindful when you build these control structure models that you might attract a security classification, and you don't really want to be sharing those raw ones with other people. Of course, right, so let's keep going. So transporting astronauts to the International Space Station. Now I've highlighted the International Space Station because we know that they are visiting the International Space Station. So there's going to be the actual space station itself, but there's going to be a control structure related to that space station, both on board the space station, who are these people on board, but also the organisation that looks after the safety and operations of the ISS. And so there is an operational organisation control structure to be thought about, and how that interacts with those in control of the spacecraft, the Starliner. And then, of course, how they make decisions, safety-related decisions, about bringing these spacecraft together. And, of course, that implies mission control, NASA mission control, and some stakeholders amongst that community. Originally planned as an 8 to 14-day mission, the crewed flight test was extended to 93 days. So that's quite a lot longer than originally planned. So it'd be interesting, just as a side quest almost, to have a think about, well, what was the original plan? What were the contingencies put in place? Was this kind of extension to the mission actually considered and properly resourced and planned for? I don't know if that's going to be discussed in this report, because I think it's just going to focus on the anomalies regarding thrust for the spacecraft. But it might reference or might discuss investigation into how that organisation actually, fared and responded to this situation. And if it doesn't, then there's something interesting there that might want to be considered from an operational safety management perspective. Okay, so it's extended to 93 days due to significant system anomalies. The Starliner capsule ultimately returned uncrewed, while astronauts Barry Butch Wilmore and Sunita Sonny Williams returned aboard SpaceX Crew 9 Dragon in March 2025. Okay, so if we were building a broad control structure, we wanted to think about the response and recovery phase and build a response control structure related to that. We might want to include SpaceX in that. We might want to include the launch and coordination of those two organisations. I don't know the detail of that, and I doubt it's discussed in this report. Because, as I say, one of the things that we always have to think about from a control structure perspective is the control structures one of the control structure's purposes, prime purposes, is to mitigate and hopefully avoid the occurrence of a particular hazard. Now, of course, if that hazard occurs and the control structure is inadequate and it hasn't prevented the hazard or the occurrence of it, then of course the control structure or another control structure has to have the responsibility of responding and recovering from the occurrence of that hazard. So whenever we define hazards, we can have straight away two high-level safety constraints. One is that the control structure must prevent the occurrence of the hazard. And then, of course, if that's not possible for whatever reason, it doesn't matter. We're not talking about probabilities here. The second high-level safety constraint is that the control structure must respond and recover to the occurrence of that hazard. And that might be the same control structure that didn't adequately control the hazard in the first place, or it could be an emergency response control structure that is stood up specifically to respond and recover. Okay, so let's keep going. So in February 2025, so this is a month before they returned, NASA chartered the Program Investigation Team, the PIT team. So I've highlighted them as a candidate for inclusion in our control structure. And the reason I've done that, again, is just to emphasize, let's as we're going through this as investigators, so to speak, let's have a think about the way that the investigation was conducted. And if we can, look at potential limitations with the investigation and perhaps recommendations for other questions to be asked or other avenues to be explored. To investigate the technical, organisational and cultural contributors to the anomalies occurring during crew flight test, the team's findings reveal a complex interplay of hardware failures, qualification gaps, leadership missteps and cultural breakdowns that collectively pose unacceptable risks to crew safety. Okay, interesting. This report was compiled and completed in November 2025, while technical cause investigation continues. Okay, so the technical cause investigation is still ongoing, that I'm aware of. So if you're involved in any of that and the stuff that I'm talking about today during this live stream or beyond can help and you want to have a conversation, please reach out. Let's have a chat so I can see if I can possibly help and move things forward a little bit. This report does not reflect any new learning or iteration of the fault tree or proximate cause through ongoing testing, analysis and discovery post-report compilation. Iteration in proximate cause is expected. So yeah, of course, as that work is ongoing, the things that are discussed in here will iterate. The key technical anomalies investigated in this report can be broken down into 4 distinct hardware anomalies. Okay, so let's have a look at those then. So we've got key technical anomalies. So the first one is the service module, the SM. I almost want to say radar cross-section. It's not radar cross-section. It's reaction control system. I'm sure it is. Thruster anomaly. 5 thrusters triggered fail off. FDIR. Let me think. What's FDIR, everybody? Failure detection. I can't remember. I should know this. It's been a long day. Let's have a look at the acronym list, everybody. Where's the acronym list? It should be just here somewhere. Why isn't the acronym list nearby? There it is. There we go. FDIR, everybody. There. Oh, that's interesting. Okay, so this definition is very slightly different to the stuff I've been looking at with the European Space Agency. It's very slightly different. So fault detection and isolation reports. So this could refer to a technical function on board the spacecraft, but it could also refer to a more broader concept of the fault detection mechanisms on board the spacecraft, and then that information being provided as feedback to the relevant controller or mission controller or whoever it is, and then they make decisions to isolate things. As I say, it's a bit ambiguous for me personally, but yeah, I'm sure if somebody's in the chat can explain what that is in detail. Yeah, thanks for that, Thomas. Yeah, fault Oh no, I'm clicking on the wrong button. There we go. Fault detection, isolation and recovery. Yes, that's the acronym I had in my mind. And it's interesting that that is slightly different. So yeah, thanks for that, Thomas. Appreciate it. See page 27. There we go. Thank you, team. Thomas also said earlier on, I missed this, sorry Thomas, AD-SWAN developed the technique for human error rate prediction, THERP, for the US Nuclear Regulatory Commission, while THERP is often characterised by the use of human event trees. Fantastic, thanks Thomas, thanks for sharing your experience. Okay, so let's just jump back to in fact what I'm going to do, whilst I've got this on the screen, I'm going to steal it and I'm going to put it near the top, because I'm going to need to use that probably many times, knowing me. So let's group that together. There we go, and I can keep it with me as we're moving. There we go. That's one of the good things about this tool. This tool is called Miro or Miro, and it's essentially an infinite whiteboard, and you can chuck PDFs in there, slide packs, things like that, and then you can annotate it and essentially make everything a big bird's nest with your brain, with your mind maps and all that. Okay, so service module, reaction control system thruster anomaly. So let's zoom in so you can see it. So we've got 5 thrusters triggered fail off FDIR during ISS rendezvous, and you'll notice I've used a blue highlight this time. And the reason I've used that is because if we're thinking through the terms or definitions of STPA, when we're thinking about unsafe control actions, one of the things we have to think about is the context within which that particular control action might be unsafe or is unsafe. And so, of course, if we're thinking about, thrusters been fired or not fired during an ISS rendezvous, of course, that context might be relevant to some of these control actions and whether they're unsafe or not. Now, of course, during ISS rendezvous is quite a broad context. So there may be other more specific contexts we need to think about or identify if we were doing an STPA. But I'm just emphasising thinking through the lens of STPA. How do we define a control action? What are the important elements of a control action? Well, one of those is context. And during ISS rendezvous is a potential candidate context we might want to think about if we were doing an STPA analysis. Okay, so during ISS rendezvous, resulting in a temporary loss of 6 degrees of freedom control. And you'll notice it emphasises their loss. So if you're familiar with the definition of a unsafe control action, let's just jump up to some slides up here. Here's some slides I made earlier. I have not added my STPA slides to this, so I do apologise, but let's just look at this. If we're thinking about unsafe control action types, there's generally 4 types. There is a control action is not provided when when you'd like it to be provided, and then there is it is provided when you probably don't want it to be provided. And of course, those two, not provided and provided, are very similar to the guide words in things like HAZOP or functional hazard assessment. And then, of course, there's the concept of provided other than just provided. So we've got timing elements. So if it's provided early or late, or it's provided too short or too long, or in the wrong sequence, maybe that's something we need to think about. Now, of course, when we're talking about loss of 6 degrees of freedom, we're potentially talking about control actions are not provided when we're in proximity to the ISS and rendezvousing. But it may be that there are other definitions that might be relevant, such as timing or duration or sequence. But of course, at this early stage of the investigation report, it sounds like we're talking about control actions that are not provided when actually they really want them to be provided. So that's interesting. That's sort of a little sort of a little indication as to the way this investigation is going to look at. So if we were doing a typical functional hazard assessment, loss of function or function failed, that's where we're sort of looking at in this case. Okay, let's zoom back in again. Let's have a look. So we've got, let's have a look. In situ troubleshooting recovered 4 of the 5 jets, enabling docking. And again, docking is potentially a candidate context if we were doing an STPA. Manual piloting. So I've emphasized that because so logically if we're talking about manual piloting, obviously there is the opposite to that, which is automated piloting, autopiloting. So when we're thinking about our control structure model, we're going to have a manual pilot, whoever or whatever that is, and we're going to have an autopilot to think about. So manual piloting did not specifically contribute to thrusters triggering their fail-off FDIR. Most probable proximate direct causes and contributing factors: two-phase oxidizer flow, vaporization and cavitation, Teflon poppet extrusion in oxidizer valves restricting flow, mechanical damage from the guidance, navigation and control firing requests. So I've underlined this because GNC firing request, I'm implying and interpreting, and I might be doing it incorrect, so if you know and you're in the chat, please give me some abuse and correct me. But in this context, guidance, navigation and control firing requests suggest that the automated, the control system, the controller, the autopilot for controlling the movement of the spacecraft, the guidance, navigation and control, provides firing requests to the propulsion system. And this, in terms of when we're building the control structure, we might look at the firing requests, control actions from the guidance, navigation and control system. But of course, if those are control actions, they will have to be manifested into the real world upon the control process, which is the spacecraft and its trajectory. So of course, if there's a mechanical demand, I'm interpreting that the control actions come from GNC, and then in terms of the control path between the controller and the control process, there becomes a mechanical demand element to it. So hardware and all of that good stuff, actual physics involved. So when we're thinking about our control loop, so let's just jump to here. We're going to be thinking about the control actions from the guidance, navigation and control system. Those control actions will need to find their way to the actual thrusters themselves. But of course, what happens between that control action being provided and what actually occurs on the control process? It could be issues with the control path, issues with the actual mechanical systems themselves. So it's not a control action issue, but it is how that control action is manifested and affects the physical control process. So we have to be thinking about that, have to be mindful of that. Okay, so where were we? Let's jump back into here. Mechanical demand from the GNC firing requests. Now you'll notice just first off, all of that is mechanical, physical. And it may be that, it's all mechanical, physical issues. It's nothing to do with the controllers and their control actions at all. It's just to do with the control path. But of course, the point of doing STAMP using STPA and CAST is to think more broadly than just mechanical failures and think about, well, how could control actions contribute to that? Either direct control actions in that actual loop itself, or more broadly and higher up in the layers of the control structure. So now the crew module RCS jet failure. So this was the service module and this is the crew module. And so logically there's going to be two automated controllers, one for the service module propulsion system and one for the crew module, and then of course they're going to have the same two human controllers on board the spacecraft, and then potentially remote ground control operators that also potentially provide control actions. I don't know what the architecture of this system is, but with other spacecraft I'm familiar with that don't have humans on board, of course there's going to be automated controller on board in that context, but of course the actual humans are many thousands, if not millions of miles away, sending controls through the ground control system. Okay, so the crew module, a thruster failed to fire during descent, reducing the system to 0 fault tolerance. Okay, so just notice that language then. A thruster, which is an actuator, failed to fire. So is it that it actually failed, or is that it is it appears to have failed, and it is to do with the control structure, the control loop. We need to think about that. And it reduced the system to zero fault tolerance. So that is a system state that is important in spacecraft design. There's a leading theory. Right, okay, so they don't know yet, but there's a leading theory. Corrosion from the carboxylic, if I've said that correctly, acid formed by residual propellant and CO2. So that sounds like a material compatibility issue. Okay, so the question then becomes, okay, let's maybe not focus on the thruster failing to fire from a control loop perspective, because we don't, we've not read the rest of the report yet. We don't know if it's relevant. But what we can say at this early stage is that if there is a material incompatibility issue, which it sounds like there is because there's corrosion, then what is the control structure around that decision to have the design as it is? Was corrosion identified as a potential concern? And was it, thought that, did they think it was mitigated, or did they accept the risk? And if they accepted the risk, what is the control structure around that decision making and how it was accepted? So of course there's this, the control structure, the local control structure involved in thruster provision, thruster control, but then there is the broader control structure that covers the design of that system and its architecture and the acceptance of potential risk. So there's something there we could probably look at. I don't expect the investigation report will have gone that far, because it says there's a leading theory. So of course, if you're involved in that investigation, there you go. There's Simon's top tip for this evening is go and look at the control structure for the decision making that surrounds that design. And of course, the second top tip is to use a control loop model, control structure model, to explore why this thruster failed. Are there contributions from the control structure, control loop itself, not just to do with physics and materials of physics of failure and materials. Okay, so the next one is helium manifold leaks. So 7 of 8 service module helium manifolds leaked during the mission. That doesn't sound very good, does it? That's really bad. So again, straight away, what's the control structure for the design and installation and manufacture of all of those parts and the design decisions about the architecture? Maybe there were known issues with the design when it was built and they just accepted it. What was the acceptance process? Why would it make sense for the organization to accept that if they knew? If they didn't know, why didn't they know? What was the control structure contribution to them not knowing when they're making decisions? So there you go. That's another top tip to try. You can have that one for free. Most probable proximate direct cause and contributing factor. Material compatibility of seals with oxidizer. Ooh, that's not good. Again, that's what is the control structure behind that decision and the acceptance of it. If it was knowingly accepted, because it's always possible it wasn't understood or known. Leading to degradation and leaks. O-ring sizing and pore gland fill squeeze tolerances. Okay, again, that's interesting. That is a design organisation control structure consideration. O-ring sizing. Maybe I'm plucking at straws here. Maybe there is a design standard, a design guidance for O-ring sizing for helium manifolds, maybe. And maybe they followed that guidance and actually it wasn't appropriate, so perhaps that guidance might need to be considered. And of course that might have knock-on effects for other spacecraft designs. I'm just sort of plucking at straws here, really just to sort of stretch your mind and help you to think more broadly, more creatively, creative thinking. And then number 4, deorbit capability fault tolerance. So the propulsion system, so you've noticed I've highlighted that in orange, that's going to be a candidate for inclusion in our control structure model. And again, it might just be, at a level of abstraction, a level of detail where it's literally just one box propulsion system. And then above that is the guidance, navigation and control system. And then above that is the human or ground controllers. Or it could be we need to expand and look inside that. Because I imagine if it's anything like the other spacecraft I've looked at, they'll have multiple controllers, primary control, secondary control and fallback and all of that kind of jazz. So it might be quite a complex architecture, especially because it's supposed to be man-rated. I expect it'll be really quite complicated. The propulsion system lacked required two-fault tolerance for deorbit burns, which was a design flaw present since early development but not identified until CFT pre-launch. So that doesn't sound very good at all, does it, everybody? So if let's think about the design organization control structure and the control structure for reviewing designs, critical review, whether it's independent review perhaps. What was the scope of that review? Why didn't that review pick it up? Because I imagine it has had independent reviews at some point, so why didn't pick it up? Or maybe it did pick it up, but it was accepted, so what was the decision making around that decision to accept it? Or maybe they didn't see it, they missed it completely, and if so, that, there's quite a big finding there. But of course it says here not identified until CFT pre-launch, so that implies that they knew that this was an issue, before they launched two astronauts into space. And so if they knew that this was a design flaw, then what was the logic behind the decision to blast some people into space? Was that really appropriate? I'm not sure. I don't know enough to context about that. But for me, that's quite a big finding that we should really look at from a detailed perspective. What's the control structure for that? Why did it make sense? I can't share. Sorry, I can't share that. Something else. Okay. So the investigation revealed multiple common findings and observations that led to key technical anomalies experienced during the CFT. I keep wanting to say combat fitness test. It's not a combat fitness test, Simon. It is a crewed flight test. Get it in your brain. Crewed flight test, not combat fitness test. There we go. These causes are outlined below. Okay, so there's key findings and observations, and this is a truncated summary. So this is a big report, and we're going to go through the rest of it on another occasion. So let's have a look then. So key findings and observations, truncated summary. So this is a truncated summary. Let's zoom in so you can see it. There we go. So number one, inadequate qualification testing. Okay, so I've highlighted orange, dark orange. Qualification testing is a function, or it's an organization that will feature in my control structure model, my preliminary model. And they will be, when I do my models, typically what I do is think about laying it out in a standard Western way of time flow. So on the left of my model, I'll have the past, so the design organization. In the middle, I'll have the operations control structure, the present. And then on the right-hand side, I'll typically put the response and recovery elements to the control structure. That's just my personal style. You don't have to do that, but I find it really helps to organize my thoughts in that fashion. So qualification testing will probably be on my left-hand side of my control structure model. And of course, qualification testing, we don't know if that's a organization function or whether there's an organization that does that, whether it's independent, includes independent qualification testing, whether it includes qualification testing for the same parts but in the past, so not these specific parts but similar ones or the same from elsewhere. The propulsion system lacked enveloping mission representative testing, and NASA accepted insufficient verification data in lieu of qualification. Okay, so that's interesting. I mean, accepting insufficient verification data, you could say that that is a type of control action. Maybe they accepted it because they believed that was the right thing to do. It made sense to them. And it's only with the benefit of hindsight we knew that was not the right thing to do. Maybe it was common practice. I'm plucking at straws here just to try and, trying to get you to sort of think and step back from, it's their fault. It's all their fault. They did some failures. It was insufficient. It's, blame, blame, blame. No, we want to take a step back and look at, why would it make sense for an organization, a group of people, an individual who is obviously an experienced person, why would it make sense for them to behave the way that they did? Not because they're all bad people or anything like that. Why would it make sense for a reasonable person to behave that way? Now, of course, there might be an argument, it might become apparent later on that there are some, and I'm not saying these people are, but, for argument's sake, there are some people that made decisions that were bad decisions and they weren't held accountable, or they were in a position of authority that they really were not qualified or should not have been in that position, then of course there are questions there over, well, what is the control structure for recruitment, selection, training and competency management of individuals? Now, of course, I'm sort of really stretching this to really get you to think very, very broadly. But on the first instance, we have to think that people come to work to do a good job. They don't want to hurt anybody, themselves or anybody else. And that's where we should start. But of course, we should always be open for the negative side of that. Or potentially, if we want to be really, really stretch this, we've always got to be aware of the potential for adversaries or potential saboteurs. I'm not saying that's in this case. I'm just saying when we're doing an investigation, we have to always be open to that, especially if the evidence we're collecting doesn't sort of seem appropriate. There's something else going on here. We have to be open to that possibility. Okay, so next one, insufficient flight data. Okay, so before we jump into that, insufficient flight data, everybody, let's just jump back to our standard control loop model, and I should probably drag it over there so it's not so far away. I'll steal that one, that'll do. Just take it over there. Zoom, 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 everybody. Right. So we've got our standard controller there, my favourite graphic, this one. There we go. So a controller provides some unsafe control actions or contributory control actions. One of the scenarios that it does that, whether it's a human or whatever, one of the reasons might be they have inadequate beliefs or flawed mental models. Process model is inadequate. Well, why might that be? Well, one of the reasons could be that the feedback, there was no feedback or inadequate feedback. And so when we're saying here about insufficient flight data is an instance of inadequate feedback. So this controller may not have been able to make decisions or make good decisions because feedback was inadequate. And that's what this is suggesting here, insufficient flight data. So we've got their low telemetry sample rates. And I've highlighted there in orange telemetry sample rates for two reasons. The first is we're talking about something in the feedback path, so telemetry. But we've also got the mention of telemetry rates. So somebody, somewhere, some organisation has made a decision that the telemetry needs to be X, Y, Z, and it needs to have a rate of update of whatever it is. I don't know. Is it once a second, once a minute, once every millisecond? I don't know. But that rate of telemetry update, somebody will have made that decision. So why did they decide that it should be whatever it is and not something that's faster? So this says low telemetry sample rates. So if it would have benefited to have faster telemetry sample rates, why did the control structure not make that happen? Maybe it was accepted that it should be a low rate because they didn't identify that it was important that that rate be increased for these kind of off-nominal situations. Okay, so lack of onboard storage. Oh, there we go, lack of onboard data storage. So somebody will have made a decision. Why did it make sense for them to do that? If it's a reused design, perhaps, I don't know, maybe some of the design is reused from elsewhere and it was accepted for speed and cost and everything else that they just have that onboard data storage. Or maybe they didn't identify that they would need more data storage. Maybe they didn't realize they needed that, a requirement for that. I'm not anticipating this report will look into that detail, but I'm hoping you can see that if you start thinking about things through the lens of a control loop and a control structure, all of a sudden you can start asking some really, really, really detailed questions without knowing necessarily the detail behind the design. Okay, so where are we going? So limited the ability to assess thruster performance and contributed to misdiagnosis of anomalies. So assessing thruster performance, that is a type of control algorithm or decision making, and that might be in this case shared between an automated controller and the spacecraft crew, the astronauts, or perhaps even the ground controllers. Maybe they were involved in those decisions. And what criteria would they need to make those decisions, which is based on the process model, the beliefs, and the availability of appropriate timely feedback. So where are we going? and contributed to misdiagnosis of anomalies. So they were receiving information about feedback, they were making decisions, and one of those decisions is about diagnosing anomalies, and they didn't diagnose them properly. So why was that? Why did it make sense? So you could do a mini control loop just for that topic, in its own right. Okay, what else? Misdiagnosis of anomalies on orbital flight test 1 and 2. Okay, so this is interesting. So we've got 2 previous orbital flight tests, unmanned and presuming, and so they had some anomalies, allegedly, according to this, apparently, but they weren't able to assess thruster performance and diagnose things properly. So that is certainly, if I was leading this investigation, that is certainly an avenue of inquiry that we'd use a control structure for. That suggests issues with the way that they've designed this, the design process, the decision making, and then of course the operational control structure for making orbital assessments and the available information to them. Okay, so anomaly resolution discipline. Acceptance of unexplained anomalies without root cause resolution allowed systemic issues to persist from orbital flight test 1 and 2 into crewed flight test. Is that what it is? Yeah, crewed flight test, not combat fitness test. There we go. I mean, that one itself, there's a whole control structure for that. You know, why did it make sense for them to do that? What was the issues with the control structure? If they don't have, I mean, it says there insufficient flight data. Okay, so why? Why didn't the control structure make sure they had sufficient flight data? Why did it not make sure that they had sufficient flight data ready to go into crew flight test? Bearing in mind, really, they should have had sufficient data for OFT2 so that they could be assured that if anything goes sideways on the crewed flight test, they have all the available information they need to make good decisions. So that to me, there's a big theme there about the way that this thing was designed, the feedback between the operation organisation and the design organisation, and how decisions were made, and how risks were assessed and accepted. So that is interesting. That particular topic from a safety management perspective, that is a big topic that really should be drilled into, in my humble opinion. Okay, so oversight and insight limitations. So I understand what oversight is, but I wasn't quite sure I understood what they meant by insight. And it's not, in the executive summary, it's not really explained. Maybe it'll be explained later on, but it would be nice to have that more clearly defined. NASA's insight into subcontractor level data was restricted. Okay, so if we're thinking about NASA being a higher level, a controller in the higher levels of the safety control structure, and the subcontractor being at a level below them, authoritative wise, the subcontractor will be providing or should be providing feedback and information and data to NASA for them to make decisions, and of course for them to provide control actions back to the subcontractor. But if that data was limited or restricted, that will undermine its ability to independently verify system readiness. Now, that might not be a big issue so long as appropriate independent verification is taking place. But of course, if it's not and it's all up to NASA, then of course that is a big issue that needs to be addressed. So yeah, that is an interesting topic as well. And I've got a bit of insight into that kind of thing in some of the other projects I've worked on. So that's very interesting. Schedule pressure, everyone's favourite, schedule pressure. Persistent proximity to launch over several... Hang on a second. Persistent proximity to launch over several years created a high-stress environment. That's not good for safety, as everyone is obviously aware. Dictated a restrictive risk reduction initiative. Okay, there we go. These are red flags in safety management. And contributed to degraded trust. Yeah, that is super bad. With the workforce and overall fatigue. Okay, that's it. Yeah, so yeah, that's interesting. Contextual factors there. Now, the thing is, the safety management system should detect those things and indicate things to the senior leadership for them to come in and do something about it. But if the safety management system is not detecting those things, or leadership are not inclined to take action, or the action they're taking is ineffective, then of course we can't really be surprised when this kind of thing happens. Okay, so cultural and contractual misalignment. The shared accountability model was poorly understood and inconsistently applied, leading to muddling of roles, responsibilities, and risk ownership. Well, of course it would. That is one of the things STAMP is really good at dealing with. So let me just go over here. Where is it? There we go. So if we were doing a CAST accident analysis, one of the parts of CAST, there are three parts of analysis in CAST. There is the physical process analysis, which includes the consideration of component failures and things like that. Then there is the controller or component analysis, so these elements in the control structure, and then of course the structure itself. And there's sort of 7 broad topics. It's not an exhaustive list, but there's basically 7 topics and whatever other experience you've got to think about. And dynamics and changes or evolution in the control structure is a big issue, but also safety culture and other environmental aspects. So environmental in this case is to do with culture and the way that people are working and interacting with each other. And if there are issues with that internally, then of course, they need to be dealt with appropriately. Why would those issues exist? Why does the control structure allow those things to exist and for that pressure to be put on people? Who's responsible for that? Do they know they're responsible for that and making it, dealing with it? Okay, so let's have another look. Where have we got to? Make sure it's big enough on the screen for you. Hardware, longevity and sparing concerns. Starliner's limited hardware spares and the impending retirement of the Atlas V launch vehicle raised concerns about the program's long-term viability. Okay. There was mention earlier on about using a SpaceX launcher. I don't know if that was only sorted out in emergency conditions to rescue the crew, or whether that was already an option. I don't know. Maybe that's a topic to think about. Okay, so the PIT also identified cultural and leadership challenges that undermine technical rigour and exacerbated technical risks. These organisational findings are outlined below. Okay. So near real-time cultural and organisational findings. So decision authority. There were overlapping roles between NASA's CCP, it's not the Chinese Communist Party, hang on, Commercial Crew Program, there we go. Commercial Crew Program, the ISSP, what's the ISSP, everybody? Where's the acronyms gone? There they are. Where's my mouse? There we go. ISSP. It's not in there. Where is it? ISSP. I'm sure, I assume it's the International Space Station Program, maybe something like that. If you know, stick it in the chat. I don't do a live Google search because you never know what might pop up, and I don't want to get my LinkedIn channel banned for something random and silly like that. So ISSP, there we go. Let's get it on the screen. So overlapping roles between the NASA's Crew Program, ISSP and Boeing led to unclear governance. Oh yeah, there we go. Thomas, thanks Thomas, you're an absolute star. So ISSP is International Space Station Program. Look at that, fantastic. So yeah, overlapping roles between NASA's CCP, ISSP and Boeing led to unclear governance. Okay, so if we were to build this using safety guided design, using STAMP, using the concept of a control structure, we would be able to anticipate those issues and put mitigations in place. I'm not necessarily saying and guaranteeing we'd be successful, but at least we'd be able to explicitly deal with it. So what are the roles and responsibilities of those entities, those controllers? How should they interact? Who has the ultimate authority to make decisions and accept risks? So again, if that stuff is not dealt with at the very top of the control structure, we can't really be surprised when bad things happen at the bottom of the control structure. Okay, so erosion of trust. So there was a mistrust between NASA and Boeing was intensified by selective data sharing, perceived favoritism, and inconsistent transparency. So this one happens all over the place. I've seen this many, many times over the years. And often it's either project managers who are under a lot of stress and are trying to limit complexity by controlling who shares what and how they share it, and they themselves get very stressed, and that leads to toxic issues. Or they don't really understand, they don't really know the detail, and so they just make arbitrary decisions without understanding the impact on people. And then those below those leaders don't necessarily have the authority or power to change their decisions. Maybe they don't have the interpersonal skills to remain an influence, perhaps, or maybe they just, they've tried many times and are just not getting anywhere, and so they just let leadership carry on. So that is an important topic that needs to be addressed. And that could be looked at through the lens of a control structure and how those stakeholders interplay with each other and the nature of the data. Now, of course, when you're defining control structures and setting high-level safety constraints, you could probably design this in the early days and say, look, these are the bits of information that are important and should be included in those data sharing agreements. And of course, there should be mechanisms for dealing with issues with transparency. Now, of course, we're talking about this with hindsight, but I've seen it in a number of other organisations, other contexts. NASA teams outside of the crewed... it's not the Chinese Communist Party, it's the Commercial Crew Programme, Simon. Come on, get it in your head. NASA teams outside the crew commercial programme felt excluded from critical design decisions, while CCP felt overwhelmed by external input. I mean, that is a really difficult thing to balance. But it is critically important that is addressed. It really does undermine trust and safety. Leadership approach. CCP and Boeing leadership were perceived as overly risk tolerant and dismissive of dissenting views. Ooh, that's interesting. I wonder how many people have resigned. I wonder what staff turnover is like. Like from a safety management perspective, one of the things I always suggest is that the safety management system has a feed from human resources and from whistleblowers and exit interviews to understand why these people are leaving, what safety issues they're experiencing, why they're not getting support. But of course, by that point, it's a bit too late. So you really do need a reporting mechanism for people to report grievances and issues, so that if they do have dissenting views, they are appropriately addressed and given the support that they need. But of course, I know that's a difficult balancing act. And of course, the toxicity of the culture is important. I'm not suggesting this is toxic, but I've certainly been in some toxic experiences in the past. And often it's not possible to wear safety issues and you just have to go. I'm not naming names. Nothing recent anyway. Team dynamics and communication. Oh, hang on a minute. Leadership and approach. Yeah, we talked about that. So risk acceptance posture created division and undermined confidence in the decision-making progress. Okay, so the risk acceptance process and the criteria, I imagine, is captured in some form of system safety management plan, which will be agreed between Boeing as the manufacturer of the spacecraft, the designer of the spacecraft, and then, of course, the NASA leadership. And, of course, that will also have to link into the operations safety management aspects, and their risk criteria, tolerability criteria, and stuff like that. So that's not good at all. That really needs looking at. What is the control structure behind all of that? Team dynamics and communications. The mission was marked by chaotic meeting schedules, unclear roles, and communication breakdowns. Okay, yeah, I mean that's really not good at all. I can understand the context and why that might happen, but this is really not good. Leaders really should have hold of that kind of thing. One of the things I'd like to emphasise as well is often there is a misunderstanding between leadership and the engineers doing the engineering, doing the creative work. Engineers and managers and project managers, typically they do management type work. So it's all about how much, how many contacts with various different stakeholders they can have as quickly as possible to help make decisions as quickly as possible. Whereas the engineers, they're typically doing creative work, maker work. And so the way that those two roles interplay has to be respectful of the intellectual, creative work that engineers do. And often engineers are detailed focused and they don't need or want distractions from what they need to do. So of course there has to be some respect between those two groups of people to make sure that the managers managing stuff need to get the attention and support they need, but likewise that shouldn't come at the expense of doing actual engineering creative work. There has to be some respect for that, and how they schedule time and schedule meetings. My personal issue is if somebody wants to book a meeting for a chat in an afternoon and doesn't say what it is, I've got basically all morning not been as effective as I could be. Whereas if the manager or leader or whoever it is was able to say, look, this is what we want to talk about. This is the the agenda, and these are the deliverables or questions or whatever, and does a bit of preparation, that means it lowers the stress level, lowers the cognitive load and cost on those creative types. But again, this is individual skills and discipline, and then how they interplay in an organisation. Yeah, but if you've got any observations or other things you'd like to share about your experience with that, please stick them in the chat. Let's hear them. Okay, so survey data shows low effectiveness ratings in team dynamics and organisational structure. So again, talking about feedback, if we go back to our little control loop, if our team is the control process and the leadership are getting these feedback surveys that are saying things are not quite good, then what are the team, what are the leaders doing? What decisions are they making? What control actions are they providing? Or are they just listening to that, or are they ignoring that and just letting things carry on? What actions did they have? That would be interesting to understand. Okay, so cultural divergence. This is interesting. NASA's traditional culture of technical rigour clashed with the commercial model's emphasis on provider or autonomy. Okay, yeah, that is a big clash. But the question then becomes, well, what is this commercial model? What does the control structure look like that? What are the safety-related roles and responsibilities for that commercial model? Have they actually been properly allocated to those stakeholders? And are they properly, enforced or constrained? There should be an agreement on that. All the findings explained in this report led the team to determining the following as root causes for the anomalies that occurred over the crewed flight test. Okay, so yeah, before I get into this, just to sort of summarise then. So there's the technical elements, but the technical elements that contribute to this accident, this incident, they don't exist in isolation. There is a whole design and operations organisation that sits above all of this that sounds rather dysfunctional and conflicts, dysfunctional with a lot of conflicts in it. So I'm anticipating that the recommendations at the end, really, really go and address those organisational issues and project issues. Okay, so root causes organisational. While these root causes are specifically separated out to bulletize each, it is nearly impossible to consider one without the others, of course, yeah. It is important to keep in mind NASA created and implemented the contract structure. Boeing built the vehicle, together the organisations agreed to fly. Okay, so this is interesting. So NASA created and implemented the contract structure. And I don't know if the investigation report digs into what the contract structure looks like, but contract structure sounds very similar to control structure. So if you were to take that contract structure, and this is one of my suggestions, and if you need help with it, give me a shout and I'll fly out and give you a hand. But take that contract structure, review it much like I'm doing with this investigation report, and try and pick out what does the control structure look like that this contract structure tries to capture in it and represent. And I would, I bet you 10 American pounds, at least 10 American pounds, that contract structure has got gaps in it, and those gaps are perhaps contributors to some of these issues. And so if you were to review that and build a control structure based on the content, find those gaps and then fill them in, and then re-update the contract structure, I think that would have a positive impact on safety. And of course, it will then have a secondary benefit for other space programs. If you've used STAMP to define one contract structure, then you could use that skill, that experience to help others. And then Boeing built the vehicle, together the organisations agreed to fly. Yes, so the control structure that provided the control action agreement to fly, I will be very interested to model that structure and see how that decision was made and why it didn't prevent this particular launch in the configuration and issues, configuration of the spacecraft, the issues with the spacecraft, and then the issues with the design and operations organisations that sit behind it. Because as I say, it's not a no-go decision based just on the spacecraft. It should be on other qualitative and quantitative feedback as well. NASA's hands-off contract approach limited insight into the Starliner's development. And I've not underlined that. So hands-off contract approach. So if we've got our control loop, and that's what it should look like. So we've got NASA there, and this is the fulfillment of the contract. I can't write today. Fulfillment. There we go, I'll put contract there. There we go. Very small. There we go. NASA is in control of contract fulfillment. If they're not doing that and it's hand off, then it's not in control. That is the definition of inadequate control. So yeah, you shouldn't have a hands-off approach. You should have a proper adequate control, whatever level of adequacy is acceptable to you. But having a hands-off approach, that's not a good idea at all. Okay, so let's move on. Actually, what I should have said is contract fulfillment. That is Starliner's development. That's what that is. Okay, what else have we got up here? So this is the last page. So it's 20:07 my time. So we've got one more page to go, everybody. We should get through this today. We'll have a quick flick through the report and then we'll schedule another time. So Boeing's inadequate systems engineering and reliance on subcontractors without sufficient oversight created gaps in hardware qualification. Okay, so Boeing being the controller, subcontractor being the controlled process, adequate systems engineering, that is a process, but of course that process is fulfilled by teams and individuals. So, why were they not doing an adequate systems engineering process? Is it because the process itself was inadequate and they were just implementing an inadequate process? Or was it a fantastic systems engineering process and they just weren't doing it very well? And if they were not doing it very well, why was that? What was the controller monitoring that and making sure they should be doing the right thing? Is it... Yeah, I think you get the picture. Without sufficient oversight. So, okay, there's a feedback loop there that was not adequate. Why was it not adequate? Or it was adequate, but there weren't control actions coming down from above, from Boeing. NASA CCP's cultural prioritised provider success over technical rigour. Yeah, okay. Why was that allowed to happen? Why didn't the control structure deal with that? Okay, so the next one then, we've got mishap classification then. So the PIT team determined that the loss of 6 degrees of freedom control during ISS rendezvous meets the criteria for a Type A mishap under NASA procedural requirements MPR 8621.1D for a loss of control flight on the docking axis due to thruster failures. Now you'll notice it says thruster failures, and I keep banging on about, well, we don't necessarily know if it's failures. What if it's dangerous successes? The system behaved as designed. The fact that it's not done what we wanted is kind of academic. Our investigation should go and look at, well, is it really thruster failures or what else was going on there? And I'd argue there's a lot of different things going on here, not just with the spacecraft, but the design and operations organisation. An alternative argument could be made to classify as a high visibility close call, since control was regained through in situ troubleshooting, which concluded in a safe docking of the Starliner spacecraft to the ISS. I think that you were very lucky something worse didn't happen, and I wouldn't tempt fate. You know, this is a Type A mishap. Let's treat it with the rigour it requires, and let's learn from this as much as we possibly can and make changes and improvements. Otherwise, this kind of stuff's going to happen again. Because organisations just don't get better overnight. There are organisations I've worked with in the past where they've had really, really serious things happen. The management say, oh yeah, we'll learn from this, we'll do this, we'll do that. And then nothing changes. It's all lip service. And I'm not saying that is in this case, but organisational change is notoriously challenging and takes time unless leadership are really committed to getting that driven home. And so, yeah, there's a lot of issues here that really need to be dealt with before the next one. I'm quite surprised actually by all of these issues. I'm not surprised because these kind of issues exist everywhere, but it's just this is such a high profile situation. We really need to sort this out. So the PIT recommends that the event be retroactively classified as Type A. Totally agree with that. And that this report serve as the final mishap investigation report. I'm not sure I agree with that because so far I've not got a warm feeling that they've dug deep enough into some of these issues. And we've only just read the exec summary, but my experience with STAMP and the concept of a control structure and a control loop, there's loads of things here that really need to be dug into and thought about. So I do recommend having a go with that. And if you do want some help or support, or you just want to have a conversation about it, please just get in touch and we can help get you on the right track. So then the final part, or second to final part then. So lessons for future programs and development vehicles. The CFT mission offers critical insights for future commercial and government-led human space flight programs. These lessons are broadly applicable to new vehicles, architectures and contracting models. Yes, completely agree with that. But I think the investigation needs to go a bit further than what we've seen so far. Design and qualification lesson. Qualification testing must reflect all mission representative environments, including but not limited to duty cycles, thermal environments, integrated system behavior, reuse, launchpad configuration, dynamic and quiescent operations, etc. Okay, yeah. Data and telemetry. Inadequate telemetry sample rates hindered anomaly detection and resolution. So yeah, I mean, for me, that should be an STPA analysis in its own right. And that would include the spacecraft designers, but also the ground controllers and how they do stuff. And I don't want to steal thunder from some of the stuff I've been doing with the European Space Agency on this other project that we're going to be reporting in the next few months. But that particular topic and being able to anticipate what type of data the ground controllers need and what sample rates they need it, is really important. And using STPA, you can define those things in advance before the spacecraft gets off the ground. And I should be able to talk about that more in the future. Organisational integration lesson. Fragmented roles and responsibilities delayed decision making and eroded confidence and trust, I would argue. Again, that absolutely needs to be nailed down. That is really, really critical. And just going back to the loop, my favourite loop over here, where is it? I'll just zoom out. Where is it? Yeah, this one here. So this loop here is slightly different to the one that you'll see in the literature. And I've included this little box at the top just to emphasise that each of these controllers has their mission-related roles and responsibilities, whatever they are, do the day job. But they also have very specific safety-related roles and responsibilities that are derived from the analysis from STPA. So, for example, making decisions about anomalies, how to detect anomalies, how to classify anomalies, whether they are important or not, what the beliefs and what the process model and the beliefs of that controller must be to be able to make those decisions, and then logically what must the feedback be to support those decisions so they can make good decisions and provide safe control actions. And of course the roles and responsibilities for that need to be made explicit. So each of these controllers should have a specific defined set of roles and responsibilities from a safety perspective, not just an operations or mission perspective. Okay, I banged on about that a bit too much now, so let's just go back. Where were we? So we were here. Yeah, talked about that. Right, so fault tolerance and hazard analysis. So a critical fault tolerance gap in the deorbit system went undetected for years. I mean, that is just, again, like I said, that needs a study in its own right to understand what the heck was going on there. Was it because they were using fault tree analysis and the reviewers of that fault tree analysis were not able to spot it because of the nature of fault tree? Was it a reused design that was assumed was acceptable because it had already been signed off and agreed, perhaps? I've seen that a few times over the years. Oh, this is safe. We're going to reuse it. Are you sure? Are you sure it's safe? I know the safety case says it's safe, but my spidey sensors, my stamp tingly sensors are telling me that doesn't quite look right. Maybe we should revisit it. Oh, you can't revisit that, Simon. It's already been signed off and agreed. Okay, if you say so. Anyway, organisational integration. Have I just said that one again, or have I missed it? Yeah, I must have missed fault tolerance one. Anyway, so number 4, organisational integration. Yeah, that can be helped using the control structure model, and then using that control structure model to show people where their roles and responsibilities are and what their control actions and feedback should be. Shared accountability and insight. The commercials model shared accountability was inconsistently understood and applied. Okay, so thinking about our control loop again. If it was inconsistently understood, that means that the process model or beliefs of those individuals or organisations was inadequate. Why was that? Is it because they had inadequate feedback? Or is it that the control actions that came from above in the hierarchy were not adequate? Or if they were adequate and the control algorithm, the decision making of those controllers was not updated to change their behaviour, why did that higher level controller not have adequate feedback to detect that and make sure that those control algorithms, decisions making mechanisms were updated and appropriate? So again, it's not just about this controller, it's about the context within which that controller sits. Because telling somebody once is not enough. Somebody to change somebody's mind and change the way they behave is not a trivial thing. It takes time, it takes repetition, and it takes support. So if there's fragmented roles and responsibilities and delayed decision making and eroded confidence, that is a leadership issue. That's not individual issue. Right. So as in the famous words of Jocko Willink, all problems are leadership problems, and that is just a good example of them. So shared accountability and insight. So the lesson, the commercial models, I've already said this one. Yeah, anomaly resolution discipline, repeated acceptance of unexpected anomalies without root cause led to reoccurrence. So yeah, why were they not doing root causes? Is it because the root cause analysis method they're using was inadequate, taking too long, or they just didn't have the right resources and people? Yeah, that certainly needs to look at. And again, I'm hoping that just from the stuff I've said tonight, you'll be thinking, well, hang on, Simon, maybe we should have a go at using STAMP as part of that anomaly resolution process, either in operations or in design and development. And if you've got some example anomalies, unexplained anomalies you'd like my help looking at, let's have a conversation. I'm sure I can bring some interest and insight based on my over 20 years experience in system safety engineering of complex systems. Okay, so we talked about that. Okay, so cultural alignment. So divergent risk assessments between NASA and providers created friction. Okay, so from a risk assessment perspective, I'd be interested to know what the criteria is for those risk assessments. And it's important to recognise as well that STAMP doesn't have a concept of risk embedded within it. It's a worst case type analysis. And of course, probability and likelihood is not included, because the main premise of STAMP is that engineered systems of this type are so complex and organised that statistics isn't inappropriate. It's unless you're talking about specific components and physics of failure, where you can think about probabilities and failure rates, then fair enough. But when you're talking about complex systems and organisations, it's almost a waste of time. So, anyway. So last two paragraphs then. So conclusion and path forward. The CFT mission, while ultimately successful, and I've said, by the skin of the teeth, by luck, it was successful. In preserving crew safety, revealed critical vulnerabilities in the Starliner's propulsion system. I mean, just say that statement. Revealing critical vulnerabilities in a spacecraft propulsion system when it's in space with people on board in proximity to the ISS. It just blows my brains. It amazes me. Anyway, NASA's oversight model and the broader culture of commercial human spaceflight, the PIT issued 61 formal recommendations across technical, organisational, cultural domains to address these issues before the next crewed Starliner mission. Okay, so that's going to be quite a delay then, I'd imagine. The report underscores that technical excellence, transparent communication, clear roles and responsibilities are not just best practices. They are essential. Yes, absolutely agree with that. To the success of any future commercial space flight missions. I think it's even bigger than that, because if you start having commercial space flight missions that have accidents in orbit, adding to space debris and everything else, and the cultural, the chilling effect that has on the culture of a nation, not just a nation, not just the Western world, but the entirety of humanity. If you're going to kill people in orbit, that's going to affect everybody. That's. I don't think we can underestimate the impact that's going to have. And then, of course, damaging, the resource of space by having space debris and everything else. We've really got to be better at this. It really must be taken more seriously. I know it's been taken seriously, but the evidence from this report that we've seen is there's a difference between reality and what we would like it to be. And I believe STAMP can help with that. I absolutely 100% am confident STAMP could help with that. The lessons from the CFT must be institutionalised to ensure that safety is never compromised in pursuit of schedule or cost. So yeah. Okay, so that's the executive summary. I'm very impressed with the broad set of issues that have been identified. I would suggest there's probably a number of those topics should be broken off into individual investigations with STAMP and considered through the lens of a control structure. Because I think there's some real learning that could be had. And of course, as we go through this report, I'm anticipating that each one of those issues is explored in detail, and we can probably build a couple of different preliminary control structures for each one and discuss it. So, of course, if you're involved in this stuff, or people who are that would benefit from this, please share this video, this live stream and the series with others. And of course, if you want to contact me, you can visit my website or go to my LinkedIn profile and just send me a message. Now, what else was I going to add? Yes, so next week, I'm going to be visiting Boston. I'll be flying out to MIT, and I'm going to be attending the 2026 STAMP workshop. If you've not been before, I do recommend it in person because you'll get to hear from the literal horse's mouth what it's all about. You'll get to hear a selection of presentations from many different people from industry and predominantly academia, to be fair, but some industry members. And of course, it's a good environment to talk and network and things like that. So I will be there next week. It is running from Monday to, I'll just zoom in so you can see. It's running from Monday the 23rd, this Monday, to Thursday the 26th. There is a schedule of various things going on. I'll just click on that. Let's see if it works. There we go. So there is quite a comprehensive program. When I say comprehensive, there's loads of stuff going on that I'm sure you'll find interesting. So let's just quickly have a look at that. And of course, if you want to contact the organizer, that's John Thomas on LinkedIn, or you can find his email address, contact details on here. But it's essentially 4 days. So the first day is about tutorials, learning the basics of stamp, cast and STPA. And then day 2 is about various different conversations, different presentations from different industries. I won't go through the whole list now, but I do recommend it. And of course, if you can't make that one, there is the European Stamp Workshop, which this year is taking place in the lovely Prague. So you can visit that. That is taking place on the 23rd to the 24th of April. So the Thursday and Friday, I think it is. Yeah, it is Thursday and Friday. And if you go into that, I'll be there as well. So come along, say hi, we can have a conversation and talk about all things system safety, stamp, STPA and cast. And of course, if you haven't already, please subscribe to my YouTube channel to be notified of new videos and of course the next live stream. I am planning to run the live stream in a week or 2 weeks after I get back from MIT next week. So we'll continue going through the investigation report. And I think we'll sort of call it an evening. I think that's about as far as we can go. So thank you very much for watching. Please remember to like, share and subscribe. And I'll see you on the next live stream. Take care. Good night.